Hey there, it's Shannon Myers, and today we'll be looking at section 11.4 from our calculus book, and that covers another vector product, the cross product of two vectors in space. So when we're done, we'll be able to find the cross product of two vectors in space and use the triple scalar product of three vectors in space. So here we go. As a warm-up, let's find these direction cosines of u equal to 5i plus 3j minus k and show that the sum of the squares of the direction cosines is 1. So let's check it out. So the magnitude of u is one thing we'll need, and that's going to equal to the square root of, let's see, 25 plus 9 plus 1, which is root 35. So cosine alpha is u1 over the magnitude of u, which is 5 over root 35. Cosine beta is u2 over the magnitude of u, which is 3 over root 35, and cosine gamma is equal to u3 over the magnitude of u, which is negative 1 over root 35. Cool so far? So those are the direction cosines. It wasn't asking us to find the angles, just the cosines. So now our verification. So these are our direction cosines, and then verification, 5 over root 35 squared plus 3 over root 35 squared plus negative 1 over root 35 squared. We want to know, is that equal to 1? So this will give us 25 over 35 plus 9 over 35 plus 1 over 35. Is that equal to 1? Yes, because we get 35 over 35, and that is indeed equal to 1. Cool, cool? All right, so definition of the cross product of two vectors in space. So here, this comes from determinants. So in general, I'm not sure if you've learned much about this. Your format won't be in the form of a determinant, but I'll just show you. If you've got your I, J, and K as your first row of your determinant, and then your second row is your u vector. This works for vectors in 3 dimensions only. And then your last row is your v components here. v2, v3. That nicer. All right. And so basically, you pick what row you want to expand about. So this is just kind of a quick and dirty way to do it. I'm going to expand about this row here. Whoops. And so when you do that, it ends up, due to cofactors, you end up alternating signs. And what we want to do is break this up into 3 2x2 determinants that are being added or subtracted. Good so far? So let's do it. Basically what you do is each time you're expanding about something, you're going to be kind of mentally crossing it out. So when I take a look at the I vector, I'm basically going to be kind of crossing out everything else and making the determinant from what's left. Make sense? So I'm going to uncross that out so that we can see everything. So this would end up being positive I I know it's in a weird spot, times u2, u3, the determinant of u2, u3, v2, v3. And then there's a negative in front of that j vector. And then, do the mental cross out. And what do you have left? u1, u3, v1, v3. And then adding the k vector. And again, the kind of mental cross out. You have u1, u2, v1, v2. And then, what does that get us? I'm going to put the unit vectors to the right side. So basically, you just multiply across. So you get u2 times v3 minus u3 times v2. That's the result of the 2x2 determinant. And then we're going to have minus u1 v3 minus u3 v1. And then that's times j. And then we'll have plus u1 v2 minus u2 v1. And that'll be times k. And that, my friends, is what u cross v is. So u cross v, that's how you pronounce it, is equal to u2 v3 minus u3 v2 times I minus u1 v3 minus u3 v1 times j plus u1 v2 minus u2 v1 times our k. Cool, cool? All right. And then just a general note, if you've got the determinant of a, b, c, d, that's equal to a times d minus b times c. And again, if you haven't had it already, you'll have it in linear. Okay, so here we go. There's some algebraic properties of the cross product. So it turns out that u cross v is equal to the negative of v cross u. And remember, unlike the dot product, when you do the cross product, remember, if you have the dot product of two vectors, you get a scalar. If you've got the cross product of two vectors, you get another vector. Oh, I'm sorry, I left out my I. I'm glad I went back here. Left out my I on that one. Okay, so here we go. U cross the sum of v and w is equal to u cross v plus u cross w, and then a scalar times u cross v is going to be either c times u cross v, this is similar to the dot product, or u cross c times v. The vector u cross the zero vector is equal to the zero vector cross u, which ends up being equal to the zero vector this time, not the scalar. U cross u is equal to the zero vector. And that's because, do you see in this formula, if you were doing u cross u, you'd be subtracting, you'd be getting zeros as coefficients. So that's why you get the zero vector. And then u dot v cross w is going to be equivalent to u cross w, u cross v dot w. So let's take a look at this one. So again, we've got these defined. We're going to have U is equal to U1, U2, U3. V is V1, V2, V3, and W will be W1, W2, and W3. And so let's check it out. U dot V cross W is going to be equivalent to, I'm just going to keep U as U for the moment. It'll be easier to write. So U dot. Now when we do our V cross W, what are we going to have? We're going to have, going back to this formula, so instead of U cross V, it's V cross W. So just looking at the formula, it would be actually, we can remember. So it'll end up being, we'll just replace the U's with the V's and the V's with the W's. No, U's with the V's and the V's with the W's. All right, so here we go. We'll have V2, W3 minus V3, W2, and that's going to be times I, minus, and then your second one will be V1, W3 minus V3, W1, and that'll be times J, and then plus V1, W2 minus V2, W1, and that's times K. Cool so far? All right, awesome. So continuing, let's see what we're going to get. We're going to have, now I'm going to put U into component form. And so we'll have U1, U2, U3 dot so putting it in component form, we'll have V2W3 minus V3W2, comma, V1W3 minus V3 W1, comma, V1 and actually they would be negatives, right? So this would be negative and this would be positive. And then because of that negative on the outside. And then we'll have V1 W2 minus V2 W1. All right, and then going through with the dot product, do you see we'll have U1 times V2 W3 minus V3 W2 plus U2 times, I'm going to switch the order of these, so, well, I'll keep them the same, times negative V1 W3 plus V3 W1. And then we'll have plus U3 times V1 W2 minus V2 W1. Cool so far? Okay, now we're just dealing with products of real numbers. So this will be equal to, now remember, I want to get to the format where I've got U cross V. And so what I'm going to be looking for is, I'm going to be looking for U2 V3 minus U3 V2, etc., right, to make it like that. And I'm going to need to basically pull the W's out of there. So let's just see what happens. I'm just going to multiply through, and then we'll group the terms that have U's and V's together and the W terms together. So we'll have U1 V2 W3 minus U1 V3 W2 minus U2 V1 times W3 minus, plus U2 V3 W1, and then plus U3 V1 W2 minus U3 V2 W1. Okay, so let's see if we can zero out any of these things. Nope. Okay, so here's what we're going to do. We're going to group together the terms that have W1s, okay? So we've got a W1 here and a W1 here. Good so far? So I'm going to factor out a W1, and then I'm going to write it as U2 V3 minus U3 V2. You see how this is going to go? Pretty cool, huh? And then next up, what do I need to do? I need to do the same thing with the W2. So here I'm gonna have, where's my W2s? I have a W2 in this term and in this term. So that's how we'll do it this time. I'm gonna add W2, and then we'll have negative U1 V3 plus U3 V1 and then the same thing with W3. So now we go to W3. And my W3 terms are here and here. So we'll have U1, V2, and then minus U2, V1. Cool so far? Well, by definition, this is what? Almost W dot U cross V, right? So here let's change this over into the format. So here we can say that this is W1, W2, W3 dot, and I'm going to, at the very end, I'm going to use the fact that the dot product is commutative, because I put the W's on the left instead of the right side. So, and that'll be dot. The first one's all good. U2 V3 minus U3, I forgot my V2 on that first one. So much subscript. All right, U2 V3 minus U3 V2 I. And then I'm going to factor out that minus, and then I'll have minus U1 V3, and I'll have a minus U3 V1. That'll be times my J, and then plus U1 V2 minus U2 V1, and that's times K. Just grouping them here. But what is that? That is W dot U cross V, and the dot product is commutative, so that's going to be U cross V dot W. Cool, cool? All right. So here we go. I had just enough space for that. Here's some geometric properties of the cross product. Right? So some interesting, cool stuff here. U and V are non-zero vectors in space, and theta is the angle between U and V. Turns out that U cross V is orthogonal to both U and V. The magnitude of U cross V is the magnitude of U times the magnitude of V, and this time times sine theta. And U cross V is equal to the zero vector if and only if U and V are scalar multiples of each other. And the magnitude of U cross V is equal to the area of the parallelogram having U and V as adjacent sides. Cool, cool, huh? All right, so let's take a look at an example. Find U cross V and show that it is orthogonal to both U and V. So let's do it. All right. So now what are we going to have? So we basically have our cross product. So remember our cross product, U cross V is equal to U2 V3 minus U3 V2 I minus U1 V3 minus U3 V1 times J, and then plus U1 V2 minus U2 V1 times K. So let's see what happens. We'll plug in our remember this is our U1, U2, and U3 vector, and this is our V1, V2 and V3. So let's do it. This is going to equal to 1 times V3 is 0 minus 2 times 1 I minus negative 1 times 0 minus 2 times 0 j and then plus u1 is negative 1, v2 is 1, minus u2 times v1, which is 0, times k. All right, so let's see how we did. We end up getting, I believe, negative 2i, and then what's that going to be? I think j zeroes out, and then we'll have minus k. How'd you do? And we can write that in component form as negative 2, 0, negative 1. Good so far? All right, so now we want to check to see if it's orthogonal. So if we do our dot product to each, u and v, we'll see if they're mutually orthogonal. So let's see. I'll do it in a different color. So u cross v dot u is going to be negative 2, 0, negative 1 dot negative 1, 1, 2. 2 plus 0 minus 2 is 0, so that checks out. And then, so that means they're orthogonal, and u cross v dot v will be negative 2, 0, negative 1 dot 0, 1, 0, and that is let's see, 0 plus 0 plus 0, which is 0. Check. So that's something to remember. The cross product of two vectors is orthogonal to each of the vectors that you use to find the cross product. Cool, cool? So these were our potential results for the cross product, and then this part was the verification. Of orthogonality. All right, so in physics, the cross product can be used to measure torque, which is the moment m of a force F, those are vectors, about some point P. If the point of application of the force is Q, the moment of the vector F about the point P is given by m, that's a vector, equals the vector PQ cross the force vector. The magnitude of the moment m measures the tendency of the vector PQ to rotate counterclockwise about an axis that's directed along the vector m. All right, well, what does that look like? So if you have this moment vector M. Okay, so let's say that we've got this vector M, and this is the axis that's directed along the vector M. So you've got some axis, and you've also got this vector M. So I don't know, let's just say that we'll have that be vertical. All right, so, and we'll say that we'll call M, I'll do it in green here. This will be M. Cool so far? And then you've got this point Q, right? Let's say this point Q is here, and then you've also got the point P, right? And we'll have this point P. We'll have him be, or her be right here, and so this directed segment here is the vector PQ. And so we're looking at how PQ, it's going to rotate about this axis that M is on. Okay? And we want to, it's going to rotate counterclockwise. All right, so I know that's kind of weird, a lot to take in, but let's just take a look at an application problem. So here in this example, we're given that both the magnitude and direction of the force on a crankshaft change as the crankshaft rotates. So we want to find the torque on the crankshaft using the position and data shown in this figure. Okay, so our Q is going to be right here. This is like our Q. It's right here. And so what we need to do is we need to figure out, okay, how is this, where is our, how is this picture relating to what we have, all right? So let's just do I, j, and k vectors. So if we make a little picture, okay, so this will be I, j, and k, and remember they're unit vectors, all right? And now let's see, we've got this, we want to find this moment vector, right? This moment vector. So what have we been given? Like, what is this right here? This segment here, right? Or actually that distance, so what do we have right here? That's probably going to be our PQ, right? The vector PQ, directed segment. And then, so with that one, let's just place this one on the K. So we're going to change our picture so that we've got our P right here, our directed segment here. This will be our Q. And so this is the directed segment PQ, or the vector PQ. Now, what have we been given here? We've also been given this angle of 60 degrees, right? So we're making a horizontal, okay, here where Q is, and then that's going to be 90 degrees, right? So we're going to bring this other segment here is going to be making a 60-degree angle to that K axis. And then this one here, of course, will be 30 degrees. So our force, this is our force vector. So our force is going to then be, force vector will be, we have going on is we'll have our force is equal to negative 2,000, because there's a downward thrust, and then times cosine 30 degrees J plus sine 30 degrees K, the way I've set it up. Good so far? All right, so F will then be, the vector F will be negative 2,000 times the vector 0 cosine 30 degrees sine 30 degrees. All right, so this of course gives us the force vector will be negative 2,000 times 0 square root of 3 over 2 and 1/2, which will give us a force vector of 0, negative 1,000 root 3, negative 1,000. Good so far? Awesome. All right. Our M vector is going to be, remember, PQ cross F. PQ cross F. So back to our deal here, we're going to be rotating about this axis here, the I-axis, and so M is going to be lying along that axis. So our M vector is going to be here. This is what it looks like. Cool so far? All right. So now, what do we do? Well, we just need to figure out what PQ is. And so PQ is lying on our K axis, right? And so PQ is going to be 0, 0, and then 0.16 given from this here, and the fact that we've put it on our K axis. All right, so PQ cross F is what our moment vector is, and so that'll be 0, 0, 0.16 cross 0, so this will be approximately negative 1732.05, and then negative 1,000, make more room, sorry about that, Okay, so then we'll have, this is going to equal to a vector, remember. And so, what's our formula? Okay, so plugging everything into the formula, right, we're going to be needing to do what, our U2 times V3. So do you see that'll zero out? So it's really the second component from PQ, right, times the third component of the force. So that's just going to zero out. So we'll end up with 0 minus, and then when we take the third component of PQ, we get 0.16, and then we multiply it to the second component. So we'll have 0.16 times negative 1732.05. That's all times I. And then minus, so what do we have next? First component is 0, so again, we'll have a 0 here. And then we need the, all right, minus. So now we're looking at what, I'm just looking at the cross product formula. So now we're looking at the first component from PQ is 0 times the third component. So this first part would be 0. And then minus, now we got to do the third component of the first one times the first component. And that'll zero out. And that's times our J. And then we'll have plus the first one would be 0 again. And then we'll have minus 0, K. Okay, so that's going to give us, let's see what that 0.16 times the other one is. So we'll get about, so these give us approximates, so we'll end up with the vector M is going to be approximately 277.1, I'll go to 0.128 times I, because that was the only one that did not zero out. But what we want is the torque, right? So the torque is what's going, measures that the magnitude of the moment vector measures the tendency for PQ to rotate. And so that's going to be our torque. So we just need the magnitude of M, which will be, there's only one of them, right? So do you see that we'll just get, we can write it out, the square root of 277.128 squared, right? Which will just be 277.128. And so what does that mean? It means that the torque on the crankshaft is approximately 277.128. Sorry, my dog has kennel cough. Poor thing. Foot-pounds. All right. So now let's move on to the next one, the triple scalar product. So if U is equal to U1i plus U2j plus U3k, and V is V1i plus V2j plus V3k, and W is W1i plus W2j plus W3k, the triple scalar product is given by U dot V cross W. So that's going to end up being equal to the determinant of U1, U2, U3, V1, V2, V3, and W1, W2, W3. So the volume of a parallelepiped with vectors U, V, and W as adjacent edges is given by the magnitude of U dot V cross W. Cool, cool? Okay, so let's just crunch some stuff out and go from there. So here, remember in general, U dot V cross W is equal to what? U1, U2, U3, V1, V2, V3, W1, W2, W3, and that's we're finding the determinant of that. So for our purposes, plugging in what we have, we're going to have 1, 1, 1, 2, 1, 0, and 0, 0, 1. It's always best to expand about the easiest row. So do you see that this one has zeros, so they'll zero out the determinants. And then doing our little trick, plus, minus, plus, minus, plus. So this will give us one times the, oops, sorry, 0 times, I'll just write it out, times the determinant of 1, 1, 1, 0 minus 0 times the determinant. So remember, we're kind of mentally crossing out those lines. So that would have been 1, 1, 2, 0, but the whole thing will zero out anyway. So you don't really have to worry about it. And then the final one is plus 1 times 1, 1, 2, 1. So that'll be 0 plus 0 plus 1 times 1 is 1 minus 2, sorry about my doggy, which will be negative 1. Cool so far? Awesome. Okay, so now let's find the volume of the parallelepiped having adjacent edges U is equal to 131.06, V is 0.66, and W is -4, 0, -4. So what we're going to do here is you're going to get a scalar, and so the magnitude is just going to really be the absolute value, right? I mean, over here, I'm thinking, let's just put a note here, which is just the absolute value of U dot V cross W. Okay, so let's find the volume of this guy. So okay, so that's what the graph that's what the vectors look like, and what happens is they can form. You can draw in this whole parallelepiped. All right, but let's find the volume. All right, so here the volume of this is going to be the absolute value of, let's say, ABS of the determinant formed by the components of these three vectors. And so again, we'll pick something easy to expand about. I'll just do this first row, and then we'll have plus, minus, plus. So we'll get, this will be the absolute value of, so 1 times the determinant 6604, and then the other one you see is just going to zero out, and then we'll have plus a -4 is still a minus a 4, and the determinant formed would be 3166. And so we'll get the absolute value of, so 1 and then 24 minus 0, and then minus 4 times 18 minus 6. So So the absolute value of 24 minus 72 plus 24, and that gives us the absolute value of negative 72, which is 72, and it's a volume, so cubic units. And we're done. All right. Cool. All right, so anyway, that wraps it up for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe. Bye.